Okay, so welcome to our third and final part of strain and material properties, closing out our discussion of chapter 2. It took us a while to get there. We kind of lingered on a few topics, but eventually we kind of worked through all the details. So today's lecture obviously is being recorded for those who are attending the career fair and can't attend in person. But hopefully, you feel free to ask questions after the fact. I think there's a few folks here, so feel free to ask questions as we go along. I'm sure it'll benefit everybody, including our viewers at home. So let's dive right into it. And, we talked about a lot of things over the past couple of weeks, really, in the discussion of strain and material properties. And I thought, what better way to wrap up that discussion than to dive into a specific example, and ideally something that'll help out with, solving some of the homework problems. So let's just consider, and I'll have to move my face out of the way here. There we go. Let's just consider a fairly simple cylinder subjected to uniaxial loading. And maybe this cylinder has an initial height H0 and some kind of cross-sectional area A0, and we apply some kind of vertical load, Fy, which, I'm representing here is just kind of a concentrated load, but suppose it's distributed evenly over kind of the ends of this cylinder. And after this cylinder is subjected to this loading, it deforms such that, as we kind of noted, in the case of many materials, when we compress them in one direction, they don't just, compress in only that direction. Usually they expand out laterally due to Poisson's effect. But basically, this cylinder will change shape. It will, shrink a little bit with the new height H, somewhat smaller than H0, and then it'll actually kind of enlarge laterally with a larger area A. So the question is, assuming that we can maybe do this kind of experiment in the laboratory, we can measure what is the applied force we're putting on this block, and we can also measure its relative change in height and cross-sectional area. Given these things, we can take some measurements and define what is the total state of strain and stress, in all of its glory, all the three-dimensional components of strain and stress. So really the question is, if we can measure these different geometric quantities and we can measure the applied force, what then are the resulting strain and stress fields inside of this deformed cylinder after we've kind of put the load on it? So let's start with strain. What would you say is the strain in this compressed cylinder? Maybe it's good to start out with what's the axial strain, or the strain along the y direction. Well, remember, how did we define strain? Well, there's a couple of different ways we could define it. In the present context, it actually is sufficient to just consider the classical definition of strain of change in length divided by initial length. So something like, in the case of the axial vertical strain, epsilon yy, or the longitudinal strain in the y direction, we can just determine it based on the change in height, or delta H, divided by the initial height, H0. Simple enough. And then what about the lateral strains? The strain in, let's say, the X and Z directions. Assuming we have these different quantities. Well, this is where it gets a little tricky. And it's kind of related to one of the homework problems, particularly that problem with the sphere that's expanding, or rather is subjected to some kind of pressure, and you want to know some details of, what's the change in, let's say, the circumference of this sphere under that applied pressure. So in the present context, it actually is sufficient to suppose that if we're trying to compute longitudinal strains, assuming small deformations, or in other words, assuming that the displacement of the cylinder is relatively small, I'm just kind of exaggerating the displacements here, we can kind of make some approximations. And in particular, I'm going to suppose that if we're really, only given these measurements of cross-sectional area and not necessarily, the diameter, we could certainly transpose these into equivalent, measurements of, the change in the diameter of the cylinder. And that would be kind of one valid way to determine what's the longitudinal strain in these transverse directions from the loading. Or we could kind of make some approximations and say, well, let's assume that this cylinder is going to deform in a fashion which is basically axisymmetric. So the longitudinal strain in any direction within the XZ plane, let's just assume it's going to be the same. So it's not going to preferentially deform laterally in any one of these directions. In which case we can kind of say, let's approximate the relative change in area based on the following. So if I wanted to know, let's say, the change in volume of, let's say, a cube of material, how did we define that change? You know, the volumetric strain. Remember what volumetric strain was? Volumetric strain, we kind of defined it as this epsilon vol is the trace of the strain tensor. And this was a valid expression in the case of small deformations. And the trace, again, is just the sum of these axial components. Okay. We can kind of do a similar thing for areas rather than volumes in this case, in which case we could say that really the change in area, or the area strain associated with the deformation of this planar surface, let's call it, you know, epsilon area, is really just the sum of now the longitudinal strains in the plane of this kind of planar area deformation. So in particular, we'll call it epsilon XX plus epsilon ZZ in this particular example. This is a reasonable approximation. And this kind of area strain can also be equivalently represented as something that looks kind of like change in area divided by initial area, where the change in area is just the difference in these two values that I've given you. So now supposing we have this, and supposing that we also say that these two things, you know, we're assuming axisymmetry, so let's assume that both of these are equal to the same value. So epsilon XX is equal to epsilon ZZ. Then we can kind of say, well, let's just say epsilon XX equals epsilon ZZ, which is just equal to this thing. And well, let's divide by 2. Such that when we sum these two things together, we get back this kind of measure of the area strain in this plane. All right, so that's strains. And obviously, you know, we could also find out what's the shear strain going on in this cylinder. But is there any shear strain? Do you think there's any shear strain going on in this particular deformation? Yeah, I'm seeing a lot of shaking heads. Hopefully you at home are also saying no. But yeah, there shouldn't really be any shear strain going on in this particular deformation. It's just uniaxial compression and then lateral expansion. So all longitudinal strains. And then stresses. This one should be pretty easy, right? If I gave you what's the vertical force applied to this cylinder, all you have to do to compute what's the axial stress in this member is take that force, divide by the area, A naught, let's say, assuming that the area doesn't change very much. You could choose A naught or you could choose A. If they're both very close in value, then you get the same, you know, resulting stress. But they do have slightly different interpretations. We won't get into that particular subject of, you know, how do you choose which cross-sectional area, the deformed one or the initial one, to use when you're computing values of stress. But for a lot of these small deformation problems, it doesn't really matter. So let's just choose initial area, just for the sake of convenience. And then what about the other components of stress? Are there any lateral components of stress applied to this cylinder? No, I'm seeing, again, shaking heads. Really, if we're supposing the only forces we're applying to this cylinder are, you know, vertical compressive ones, we're not confining it laterally, it's just going to expand outward, and there's nothing that resists that. So in that case, there's really only this uniaxial state of stress, which basically means I have states of strain and stress that look kind of like this. So I have, let's say, you know, basically a Y stress, it looks like that. I have these longitudinal strains as I previously derived, and then all the other components of strain and stress are equal to 0. Okay, well, that's fairly straightforward. But remember from last lecture, we talked about this notion of deviatoric and volumetric measures of both strain and stress, which were kind of useful ways of decomposing both the strain and stress tensors into these, you know, basically separable deformations that can be, you know, connected via totally independent constitutive relationships. So the volumetric strain can be linked directly to volumetric stress, or the average stress in this piece of material, assuming it's isotropic and linear elastic. And the deviatoric strain, which is a volume preserving deformation, can be linked directly to the deviatoric stress, which was kind of a state of pure shear. So if I asked you, what are the different representations of the volumetric strain in this material, as well as the deviatoric strain, how would I compute those things? Well, we already have volumetric strain, right? This one should be pretty direct. It's just the trace of the strain tensor. So take all these longitudinal values of strain that we've already determined, and then just sum them up, and that's volumetric strain, or a measure of the total relative change in volume of the cylinder. For the deviatoric strain, maybe this was something that was glossed over in last lecture, but if we wanted to know what's the deviatoric strain, really we just have to take the original strain tensor, something that maybe looks kind of like this. Take the original strain tensor, the full, array of values, and then subtract off 1/3 times the volumetric strain times the identity tensor. So it's kind of like you basically just need to take the original strain tensor and then remove from the diagonal entries of that strain tensor 1/3 of the volumetric strain. Fairly easy. So basically remove the average part of the total strain, and that's how you get deviatoric strain. Fairly straightforward. In fact, this is fairly similar to how we would determine volumetric stress by a similar procedure. The average stress is just 1/3 of the trace of the stress tensor, and then deviatoric stress is really kind of the same thing. Basically just take the original stress tensor and then subtract off the average part. And that's how you would determine these different types of stress and strain. So we could do that as in this particular example, and what we would get is something that looks kind of like this. So the volumetric strain is really just, again, the trace of the strain tensor. Just sum up all these values and we get something that looks like this. We can kind of rearrange terms and simplify it, and it looks a little bit like that, involving these different measured quantities associated with the deformed and undeformed configurations of the cylinder. And we can do the same thing to compute what's the average stress, or kind of the mean stress. You can think of this as kind of like the hydrostatic pressure inside of the cylinder. Although if you look in the book, they define pressure as basically a, sigma average with a minus sign. So that's kind of the only distinction. Pressure usually has the interpretation of being a positive value when it's in a state of compressive pressurized loading. That's, fairly typical of a lot of, fluids or other types of materials that can only sustain these kind of hydrostatic pressure-like forces. And it only really makes sense to consider them under compressive loading conditions. Hence why that negative sign shows up in the definition of pressure. All right, so we can compute the average stress, and then we can compute the deviatoric stresses just by basically taking the original strain and stress components and then subtracting off of those the average strain and stress to determine deviatoric strain and deviatoric stress. They're individual components. And it turns out for this particular special type of loading, the deviatoric strain increments, or rather the deviatoric strain components, will all kind of have more or less the same value. They'll just have slightly different scalings. So the deviatoric strain in the y direction is really equal to -2 times the deviatoric strain in the x and z directions. And there's kind of a similar relationship for deviatoric stress in this particular case of uniaxial stress. And this is kind of a specialized case. All right, so now we know what are the components of deviatoric strain, deviatoric stress, volumetric strain, as well as the average or volumetric stress. And now remember what we discussed kind of late last lecture, this notion of strain energy, which is kind of like a measure of how much work do I have to do to deform some kind of unit of material. And really, it's strain energy density. It's the amount of work I have to do per unit of volume of some kind of small chunk of material. And we define strain energy as basically, the, sum up of all of the incremental, amount of work that we have to do as we continue to stretch the material from an undeformed state into a fully deformed state. And it turns out that was really just equal to basically, 1/2 the stress tensor times the strain tensor multiplied through this kind of specialized inner product, or a tensor contraction. So it's basically just sum up the product of all the individual multiplications of the stress components times the strain components. But there was also a nifty way that we could decompose this kind of definition of strain energy into two totally separable parts, the volumetric part and the deviatoric part. And we defined volumetric strain energy as basically the part of the strain energy that is attributable solely to these kind of volumetric deformations, and the deviatoric part is associated just with the deviatoric deformations. So the volume preserving deformations, that is. So we could come up with these different expressions. I won't bore you with the details, but it looks kind of something like this. So remember these definitions: volumetric strain energy density looks kind of like this. 1/2. Now, not just, the strain and stress tensors multiplied together, but specifically in the case of volumetric strain energy density, it's the average stress multiplied by the volumetric strain. And the deviatoric strain energy density is just 1/2 the deviatoric stress multiplied by the deviatoric strain, using this kind of funky, double dot inner product thing. We'll talk a little bit more about some of the details of that later and revisit that and expand on it. But suffice it to say, you can do these different computations in a fairly straightforward way. Just take the individual components of, let's say, in the case of the deviatoric strain energy density, take the individual components of the deviatoric stress, multiply them by the corresponding components of deviatoric strain, and then sum those different products all together. So there should be a total of 3 different terms for each of the 3 different components of deviatoric strain and stress that you multiply together, and then you sum up all those products. And that's how you get deviatoric strain energy density. And then volumetric strain energy density, fairly straightforward. Just multiply average strain and volumetric strain and volumetric stress. There's a lot of different ways you could name these quantities. All right, but what if I wanted to know something more? Really, this whole discussion and, kind of the lead up from the last lecture was noting that, these materials have these quantifiable properties, these kind of elastic properties that we want to be able to measure, ideally through kind of simple experiments, kind of like this. So if you were to go into the laboratory and you can measure all these things directly, you have some kind of piece of testing equipment that's calibrated so you can measure the amount of force that you're applying. You can also go in and actually measure what's the change in height, what's the change in cross-sectional area of this specimen, let's say, like a concrete cylinder perhaps. And you can then say, well, now I've taken all these measurements. What can I do with that? How do I quantify these different elastic properties that we've talked about in the previous lecture? So the question is, in this specific example, maybe I ask you not necessarily what's the Young's modulus or Poisson's ratio. Maybe you can figure out how you would compute those specific things in the case of a uniaxial stress scenario. But what if I instead ask, what's the bulk modulus and the shear modulus associated with this chunk of material? Could we use all the things that we've just computed and then determine what those quantities need to be? Well, how would you go about actually determining what are those different elastic constants given these measurements? I'll give you a little hint. Suppose we could measure these things. Suppose, we had a stress strain plot. As we're loading up these different things, we can compute what's the amount of applied load that we're putting on this thing, and we can compute at different stages through the loading. How is, the relative height of this cylinder and its cross-sectional area changing? And then from that, we could say, well, from these different quantities, I've already kind of derived things like how does the average stress vary in relation to the volumetric strain. Both of these things are quantities that we've kind of developed expressions for. And if we were to look at different kind of stages of the loading process, we could see that, maybe we take these discrete measurements and we notice, wow, they're actually linearly correlated like this. So in other words, volumetric strain and average stress should both kind of be increasing proportional to one another as you increase the applied loading. And the resulting slope of this kind of measured curve, if you were to kind of like plot it in this 2D format, the slope of this curve would be precisely the bulk modulus. Or in other words, basically the measure of how does average stress relate to volumetric strain. So bulk modulus, basically, if we just take some reference point where we say, let's just initialize volumetric strain and say it's 0. Same thing, let's initialize average stress and say it's 0 at this point, and then take some other point at which we've increased the load. We can basically define this kind of straight line. We can determine what's the slope of that line. And then all we have to do to determine what's this stiffness coefficient is, take basically the change in the stress divided by the change in strain on this kind of like two-dimensional plot. And if, the initial values were 0, then it's just, in this case, sigma average divided by epsilon vol at the final deformed state. We could do a similar thing to determine what's the resulting relationship between deviatoric stress and deviatoric strain. We could do it basically just for a single component of the deviatoric strain and deviatoric stress, and kind of do a similar procedure where we basically quantify what's the shear modulus now as kind of like the ratio of, the relative change in one of the components of shear stress and the relative change in the corresponding component of shear strain. Now, it looks more or less like this, and we would leverage precisely these relationships. So assuming you have, some assumed relationship in terms of the bulk modulus and assumed relationship in terms of the shear modulus of, volumetric strain and deviatoric strain to volumetric stress and deviatoric stress, we basically just compute the ratios of these different quantities and we get something that looks like this. So purely from this experimental data, and making a few different manipulations in terms of how we represent stresses and strains in terms of these two decomposed deformation modes, we can then directly determine what are the bulk modulus and shear modulus of this chunk of material. So that's pretty cool. From this single experiment, we totally characterize the elastic properties of this specimen. Very cool. Much easier than having to run 36 or who knows how many experiments to try to characterize all those different components of that kind of elastic stiffness matrix that was, huge. And, the nice thing about isotropic elasticity, if you assume that the material behaves in this kind of isotropic fashion, is that you can run basically just one experiment, and that's really all the information you need to characterize the elastic behavior. All right. Now, here's an interesting and kind of fun question. Are there any restrictions that we should place, physical limitations or considerations that might restrict what the potential values of the bulk modulus and shear modulus should be for this material? It's kind of not something you might have to chew on and just think through a little bit. I mean, it makes sense for this particular slope to be positive, right? It wouldn't really make sense if, let's say, bulk modulus was negative. Like the situation that you would need to have if you had basically a negative slope in this curve would be that if you were to try to expand some piece of material, it would actually generate some kind of, compressive stress. Or conversely, if you tried to pressurize some kind of sphere of material and somehow you pushing on it actually causes it to expand, that would be basically a negative bulk modulus, which makes very little physical sense. I mean, there may be some weird kind of mechanical engineer working on like these interesting metamaterials that exhibit these unusual negative stiffness properties, but for almost all physical materials, these stiffness coefficients, both the shear modulus and the bulk modulus, And, Young's modulus, Lemay's constant, and all those things, they should really be positive values. And again, it kind of boils down to this. If you pull on something in one direction, you expect a corresponding stress to develop in that same direction. That's kind of a fairly intuitive result. But, let's kind of examine this a little bit further. And it might be useful to consider not necessarily examining the constraints that we put on these individual coefficients of bulk modulus and shear modulus, but rather their ratio. So suppose we took the ratio of the shear modulus divided by the bulk modulus. And if you look at the expressions that we've just derived, you'll notice that there's a lot of similar terms. There's dependence on the axial load, there's dependence on the height of the cylinder and some other quantities. So a lot of things are actually going to cancel out when we take this ratio and simplify to the point where we can actually represent things in terms of, very simple, just purely geometric quantities. It has nothing to do with the loading. And what's even more interesting is we can simplify it yet further and come up with some expressions that look kind of like this. So, transforming some of the relationships we developed earlier to express, the longitudinal strain in these different directions, we come up with these kind of final expressions that look kind of like this. And we can connect some of these things together by supposing that, remember that thing, the Poisson's ratio? It's basically a way of relating longitudinal strain in the direction of loading to the, transverse strain that occurs, transverse to the loading direction. So Poisson's ratio is kind of just a way of relating longitudinal strain in the axial direction of loading to transverse strains. So we can use that to kind of further actually reduce this expression and come up with a final relationship that actually connects these different elastic constants to one another. So now we have an expression that relates shear modulus, bulk modulus, and the Poisson's ratio, this other constant that we kind of said was of interest for characterizing elastic behavior. And this expression basically implies that not all of these different parameters are independently defined. So in other words, if you knew what the bulk modulus and the shear modulus of this material were, it basically means that the Poisson's ratio is not an independently defined quantity. If you know G and you know K, then nu should really be determined by this expression. Or conversely, if you knew G and you knew nu, then K would also then be defined through this expression. So really, this is kind of an important indication that not all of these different elastic constants that we've been talking about, Poisson's ratio, Young's modulus, bulk modulus, shear modulus, Lemay's constant, they're not independently defined. They actually have certain constraints imposed on them. And this is just one of them. We'll talk about a few others. But the idea here is that, we can actually quantify these relationships in this kind of interesting way and use them to figure out what are the other constants given some known or quantified values of the others. So what's interesting is that we can kind of take a closer look at this relationship between this ratio, between the shear and bulk modulus, and the Poisson's ratio. So let's do that. Let's actually consider what happens if we plot kind of in an XY diagram, let's say the Poisson's ratio on the x-axis, and this kind of ratio of G over K on the y-axis. And let me move my face out of the way. There we go. That's better. Okay, so let's see what happens. What are some practical limits? Revisiting the question of what are the practical limits that we should place on these different elastic constants. Now, I said, it makes sense that G and K should be positive values. Okay. Now, what happens if, I don't know, this ratio, G over K, let's say, I don't know, G becomes, well, what do we want to say? Let's say G becomes really small, or let's say K becomes really big. Some situations where that's the case are basically materials that have very, very low shear modulus. So they're very easily deformable in this kind of mode of a volume preserving deformation. But by comparison, they're relatively incompressible in the sense that they have a really, really big or comparatively big bulk modulus. There's a lot of materials that behave like this. Rubbers or other kinds of polymers of that nature, Water is usually characterized as a kind of incompressible material. It has a relatively large bulk modulus, and by comparison, the shear modulus is very low. So it kind of deforms in this funny way, but it overall preserves most of its volume when it deforms. So such materials characterize this incompressible behavior. And really, that situation where either bulk modulus gets really, really big or shear modulus gets really, really small implies that, that ratio will go to zero. But it'll tend toward a limit, basically. And it'll tend toward the limit where the Poisson's ratio, in fact, will approach a value of 1/2. Now, you can't make G any smaller than that, because obviously it still has to be a positive value. So really that's as big, that's as small as we can kind of make that particular ratio. It can only be basically, 0 at a minimum, which basically means that at a maximum, the Poisson's ratio can't be bigger than this value of 1/2. And in practice, it never actually really achieves that limit. In practice, there's always at least a little bit of, residual shear stiffness, or, basically the shear modulus is never quite exactly 0. And the bulk modulus is never quite exactly infinite. There's no such thing as a truly incompressible material. Everything is just a little bit compressible. So in that case, you never really achieve this kind of true limit of incompressibility. So it still provides a nice upper bound on what the Poisson's ratio can be. And it provides kind of a connection to, how does it relate to the relationship between G and K? Now, what's also interesting is that for most materials, not all materials, but for most materials, the Poisson's ratio will usually be in the range of, somewhere between 0 and a value of 1/2. A value of 0 basically means that if you had this cylinder, if you were to kind of like stretch it in the axial direction, it would expand, vertically, but it wouldn't undergo any Poisson's effect. That corresponds basically to the case of Poisson's ratio equals 0, right? So there's no lateral contraction or expansion when you load it in some kind of axial direction. At that particular case, the ratio of the shear and bulk modulus has to be equal to 1.5. That's kind of just by virtue of how we've related these different elastic constants to one another. If you happen to have a situation where, I don't know, let's say someone came to you and said, here's a shear modulus, here's a bulk modulus, but you found that actually the shear modulus was substantially larger than the bulk modulus. Somebody said, oh, let's just say shear modulus equals 100 and bulk modulus equals 1 or something like that. It would basically imply that you're off the chart on this. It would imply that the ratio is 100:1, which would also imply that Poisson's ratio is actually a negative value according to this relationship. So sometimes if you're trying to independently set these different constants, there may not be physical settings for them. And you should probably consider like, what are some of these physical constraints? Maybe check the other elastic constants and verify that they actually make intuitive or physical sense. All right, so I think that's enough of this particular example. Kind of interesting. I will say, though, that as I had mentioned, there are not necessarily, not all of these different elastic constants that we've discussed are independently defined. And in general, if you happen to know 2 of them, let's say if you knew Poisson's ratio and Young's modulus, then there are other expressions that you can derive to determine what these other coefficients need to be in order to kind of satisfy, these kind of independently defined relationships. So technically speaking, assuming you know 2 of these elastic constants, you can kind of use these different relationships to determine what should the other constants be. So pick 2, set their values, and then you can find the others based on those kind of settings. A nifty table that I'll kind of point to, and there's a lot of different iterations and versions of this table that you can find online. But if you happen to know, let's say, bulk modulus and shear modulus, you can find formulas fairly easily online, or this particular table is a good example of how you would convert from those known constants into the other values. So it makes the process a little bit easier. I've seen people who keep a little cheat sheet version of this like pasted to their desk because they use it so frequently. It's like, they're setting up like analysis models in some kind of finite element code, and it's just, indispensable to kind of be able to convert between these different elastic constants. So if you want to have something that you take away from this class, this might be a nice thing to kind of like, I don't know, paste on your desk, or maybe on your wall, or have it somewhere handy. All right. So with that, I wanted to kind of close out the discussion of this particular chapter with a slightly deeper dive on the subject that we brought up in last lecture regarding this interesting, let's call it this interesting tensor inner product, or the tensor contraction, which we used to define the elastic strain energy density. Remember, this kind of double dot in between the stress and strain tensors basically implied that we were taking the sum of the products of the individual components of the stress and strain tensors. And there were a bunch of different ways that we could write that out and represent that. We could write it in this index notation format where implicitly we're kind of writing the sub-indices of the components of stress and strain that we're multiplying together. And then we represent it as this kind of double summation over the full range of values for the sub-indices I and J, ranging from I and J between 1 and 3, let's say. We could write it in this kind of full-on matrix representation of the stress and strain tensors and expand it out in terms of like the explicit representation of what that kind of sum of the products of the individual components of stress and strain actually looks like. And that's all well and good. Now, I'm going to start diving into what I'll call maybe more in-depth discussion of index notation and some of the rules attendant to it, and how we can use this tensor contraction symbol in another context that's particularly relevant to the discussion of material properties. So first of all, let's kind of take a few preliminary steps. I want to kind of dive into and kind of remind you of this notion of Einstein's summation convention, which is basically the idea that if you have this expression represented in terms of these sub-indices, in general, if you're trying to represent, this kind of tensor contraction in terms of this double summation over, sigma ij, epsilon ij, where these ranges for I and j range between 1 and 3, Einstein and various other people who came after him were actually quite lazy. They didn't want to have to write this double summation, like these sigma symbols and the ranges for those values, because they were doing it all the time. And there was a lot of hassle in kind of writing that out. So instead, they came up with this nifty shorthand, the Einstein summation convention, that basically said that if you have an expression that looks kind of like this, that involves basically the product of two tensor-like quantities, and if you represent their indices in terms of, let's say, I and j subscripts, suggesting that you're kind of iterating over particular values of I and j, then in this expression, if there is, let's say, a particular index I, in this case, that is repeated in this expression, then the implication is that I can basically write out this expression by omitting the summation over I, that big summation symbol, just forget about it. And it's just implied that we're actually taking the sum of the product of all these values for I ranging from 1 to 3. This is kind of one of the fundamental rules of index notation and Einstein summation convention. So anytime you have a repeated pair of sub-indices in one of these kind of expressions for the product between two tensors, it implies that there's actually a summation happening. So that's kind of why I've represented these summation symbols in gray. I could equally well just omit this kind of set of summation symbols, and by Einstein's summation convention, it's implied that there's still a summation happening over this kind of range of different indices. All right, same thing for J. If J is repeated, it's also kind of treated as there being an implicit summation over J equals 1 to 3. All right, now a few other things. You'll notice this in some of the literature and some other sources, and I think it's particularly convenient to do the following. Rather than represent all the different sub-indices of these tensors in terms of x, y, and z subscripts, it can be a little bit confusing if you have, let's say, letters to represent these indices. But really, when you plug them in, to say, let's say I equals 1 to 3, it makes sense when you're defining ranges over, integer values of this kind of summation. So in many cases, you'll notice that the subscripts for, x, y, and z in the definition of these tensors is just replaced by 1, 2, and 3. No, it's kind of a minor change, but it's relevant because, you'll see why. You'll see why. So just kind of blur your vision and say if there's an x, y, z subscript, just replace it by 1, 2, or 3. They mean the same thing, at least if we're kind of representing tensor components now in terms of these indexed kind of iterative, products between values. All right. Now, the other interesting thing, and the particular use of this, tensor contraction operator is to basically say that, kind of like we did before when we were talking about the definition of particular components of stress as being basically the sum of all these different components of strain multiplied by a bunch of different components of this kind of like elastic stiffness coefficient matrix summed together, and that gives me a particular component of stress. It turns out that, we could do that same kind of representation like we did before. We represented everything in terms of this kind of like vector of stress components is equal to some matrix of stiffness components times the corresponding vector of strain components. We can write it in that kind of vector matrix format, or equivalently, we can write it in terms of this index notation. And the textbook actually provides exactly this expression. So if you came across this when you were reading through chapter 2 and you saw this expression that looked like sigma ij equals Cij_KL epsilon KL, this is really what they meant. There's an implied summation over K and L, which basically is equivalent to saying that if we want to know what's the particular component of stress, let's say sigma ij, where I and j are equal to 1 and 2. So sigma 1, 2, or sigma xy. For that particular component of stress, we can determine what is that component of stress expressed in terms of this tensor contraction between all the components of strain and some, let's say, subtensor comprising this collection of elastic stiffness coefficients that would show up equivalently in that big kind of matrix that we'd established, that 6 by 6 array of stiffness values. So this is just kind of an alternative way to relate the independent components of stress to the corresponding components of strain. In general, all the components of strain will kind of affect potentially a given component of stress. And this is true for all values of sigma ij, where I and j range between 1 and 3. So we can represent components of stress in this fashion using this kind of tensor contraction operator. And we can construct this larger, let's call it the elastic stiffness tensor, which is basically an array of arrays, which is kind of a mind-bending concept. But suppose, you were to visualize it in this way, where you wanted to know what's the resulting stress tensor given some known components of the strain tensor. You could write it out in that kind of matrix vector representation like we did previously, or you could represent it in this kind of symbolic notation in terms of these tensor quantities, a stress tensor, a strain tensor, and this material stiffness tensor. Now, really, it's not just a tensor as we're used to thinking about in the case of stress and strain tensors. Stresses and strain tensors are these two-dimensional arrays, right? The elastic stiffness tensor is really a tensor of tensors. So if you think about it, it's kind of like it's a 3 by 3 array, and each of the sub entries in this 3 by 3 array is itself a 3 by 3 array. So you could also think of it as kind of being like this 4-dimensional array, if you like, which has kind of subscript indices ranging over each one of those 4 dimensions, I, j, k, and l. So in total, this kind of 4-dimensional array or tensor of tensors is going to have a total of 3 to the 4th or 81 individual stiffness components, which you can use to basically individually figure out, through a tensor contraction operation of any one of these subtensors with the strain tensor to give you the corresponding component of stress. And you can do that for each component of stress. that's kind of the interesting utility of these things. And it can be represented entirely in terms of index notation, in terms of this big expanded array of array thing, or in terms of this very nicely compact, direct tensor notation with the aid of that kind of tensor contraction double dot symbol. So different ways you can represent basically the same thing. Now, the other kind of interesting thing is in the special case of isotropic elasticity, remember, there were really only two unique elastic constants, which meant that a lot of the representation of the entries of this kind of array of arrays for the elastic stiffness tensor basically are zero or can be represented in terms of a reduced subset of elastic constants, like the Lemay parameters. The Lemay first parameter, lambda, and the shear modulus. And we can arrange it like so. It kind of looks fairly convenient. And you'll notice some interesting properties about the elastic stiffness tensor. In terms of this kind of array format, you'll notice that each one of the subarrays is symmetric. So if you were to take, I don't know, the entry corresponding to the first row and the second column, you'll notice that basically, these values are symmetric. And that's true for basically all of these submatrices. You'll also notice that, this kind of full array is also itself symmetric. So if you were to swap this kind of sub-entry with this sub-entry, those two tensors, they're actually equal to one another. These are kind of referred to as the minor symmetries of the elastic stiffness tensor, which basically implies that if you were to swap those different components, basically flip this tensor or flip, the representation of these individual entries, you would get basically the same thing. So it's an interesting property of the elastic stiffness tensor. But at the end of the day, we can still represent it, in a much simpler format. We don't have to always represent it in terms of this very general fourth order, tensor kind of thing. Oftentimes it's sufficient to just say, well, let's represent in terms of these two unique, isotropic elastic coefficients. Now, the last thing that I'll say, which is kind of interesting, is if you wanted to represent, let's say, the individual components of this particular stiffness tensor, this kind of fourth order array, how would you do it? We have these expressions, let's say in this case, where we have sigma ij equals implied summation over KNL ofCijkl multiplied by epsilon KL. So how exactly would we represent,Cijkl, assuming we happen to know just G and lambda? Well, there's one way that you can demonstrate this, but I won't walk through all the details. But the final result looks something like this. It's possible to actually express this kind of four-dimensional array in terms of G and lambda, yes, and in terms of these kind of delta symbols, sometimes referred to as the Kronecker delta. And don't be intimidated by the name. The Kronecker delta is really just the identity tensor represented through index notation. So delta ij is basically just 1 on the diagonal when I equals j, and 0 otherwise when I is not equal to j. So imagine just a simple 3x3 array, 1's on the diagonal, 0 is off diagonal. So it's really just the identity tensor. So through some combination of interesting permutations on the subindices for the identity tensor in different combinations, multiplied by these different elastic constants, we can then come up with this full representation forCijkl. And you can imagine why you would want to go through the trouble of using this kind of weird index notation kind of thing, because especially when you get into the subject of anisotropic materials, where it's no longer possible to reduce everything down into just, G and lambda. Now you have a bunch more constants you have to worry about. And in general, the representation of the elastic stiffness tensor becomes a little bit more complicated. In those cases, it really is useful to be able to rely upon index notation so that you can write something like this or this without having to basically write this entire thing. Can you imagine how much time that would take to write in all these entries of this big array? Too much time. So for shorthand, it's useful to rely on index notation to kind of be particular about what the individual entries are, but while still kind of avoiding the hassle of writing it all out explicitly. So a lot of utility with index notation. I don't know how much we'll actually kind of,
make deep use of it, but I want you to at least kind of understand the basics of it, because if you go into like some of the theory manuals of various finite element codes like Abacus or ANSYS, sometimes they'll describe some of their material models using this particular notation. And it can be a little confusing if you haven't been exposed to it, but if you have at least some of the preliminary background to understand it, it can be really useful. All right. So now, switching gears, we've closed the chapter for chapter 2 on the discussion of strain and material properties. Not that we're leaving it behind, but we are moving on to other more interesting subjects. I think you've probably gotten fairly fatigued with the discussion of the analysis of stress and the analysis of strain. Okay, you know, it's a lot of math, it's a lot of background, but let's actually get to solving some problems. You know, you probably came into this class thinking, oh, I thought this was going to be more about solving engineering problems, right? So to deliver on that promise, let's dive into that. And this is really the chapter where we start to actually solve a few interesting problems in mechanics, and in particular, you know, the three-dimensional theory of elasticity. So without further ado, we'll cover a bunch of different things. We'll see how much time we have to go into detail on these different subjects. But we'll talk about, first of all, boundary conditions. What are boundary value problems? How do we solve them? And, you know, restrictions to two-dimensional states of plane stress and plane strain, different approaches for how you solve these different problems, and then particular examinations of, you know, how do we actually apply this theory to solve interesting problems? Like, what happens if we have a hole inside of a member? How do we determine what's the resulting stress field? Or, you know, what happens if we have stress concentrations due to like localized contact between members? We'll talk a little bit about that. So we'll kind of try to go through most of this. But before we dive into all that, we really have to kind of review what exactly have we taken away from chapters 1 and 2? And how does that equip us to solve some of these problems now in the theory of elasticity? So remember, you know, what is it that we really covered? And I'll remind you of the governing principles of mechanics, as I kept reiterating and kind of trying to drill into your brain. There was a good reason why I tried to do that. And it comes down to this. All of chapter 1 and 2, really, if you like, can be reduced down into just this slide. It's compatibility. The implication that if you have some kind of continuous displacement field, that you can relate the displacement field, you know, a vector of individual displacement components that varies spatially. You can relate that displacement field to some resulting strain field through our strain displacement relationship, the thing that we derived, you know, at the beginning of chapter 2, that says the strain tensor is really just the symmetric part of the displacement gradient, or if you like, 1/2 of displacement gradient plus its transpose. That's the symmetric part. And that gave us 6 relationships that basically said that if I know what the displacement field looks like, I can figure out what the strain field looks like. So the strain field is not an independently defined field quantity. It is defined, you know, assuming you know what the displacements are, non-uniquely through this relationship. Then we had the constitutive law, the second part of chapter 2, the relationship between stress and strain. And we could write it in terms of this fancy tensor notation that we've kind of established, or in the case of isotropic elasticity, we could represent it in terms of this more compact representation. So that gave us 6 equations, if you like, or relationships between the 6 independent components of strain and the 6 independent components of stress. So if you're kind of keeping count here, there's a total of now 12 equations or relationships that we've established from these 2, you know, strain displacement relationships and stress strain relationships. And then finally, we had equilibrium, the subject of chapter 1, which basically said, you know, okay, well, let's just assume that moment equilibrium is automatically satisfied if we enforce that the stress tensor has to be symmetric. So if we always assume that, and if we always represent the stress tensor as a symmetric tensor, we never actually have to worry about moment equilibrium in the case of at least solving these elasticity problems, which is maybe a little bit of a departure from how you're used to thinking of solving equilibrium problems. You got to have force and moment equilibrium. But in the case of elasticity, moment equilibrium comes for free, almost, assuming that you enforce that kind of symmetry condition on the stress tensor. It's a local condition enforced on basically every small chunk of material in the body. Assuming it's symmetric, you satisfy moment equilibrium. But force equilibrium was the thing that we had to kind of come up with this extra equation or set of equations for. And we came up with these three sets of force balance equations governing force equilibrium in some body that might have some variable stress field and also maybe some variable body force field, where B is a vector of, components of body forces that might act in the X, Y, and Z directions. And body force, again, think of it kind of like self-weight. So all these different equations, in total, 15 equations. If you're keeping track of what some of the homework problems we're asking, you'll probably recall that the 15 equations of elasticity, when they ask you to verify, are those different 15 equations of elasticity satisfied? This is really what they mean. Just strain displacement relationship, stress strain, and then the force balance kind of equilibrium equations. So if you verify these, then you're done. You don't have to do anything more. But as I mentioned, not all of these quantities are independently defined. We have a direct relationship between displacement and strain, and a relationship between strain and stress. So really, if we wanted to, we could kind of like combine them all into one glorious single governing differential equation, one equation to rule them all, and in the darkness bind them. And in this case, it's the expression on the right-hand side. So the governing differential equation of elasticity can be expressed by basically just, substituting these different fields into each of these subsequent expressions. So replace, the strain with the symmetric part of the displacement gradient, replace strain now in terms of the displacement, to get stress in terms of displacement field only. And really the only field that we should be using to represent this kind of solution, the thing that we're solving for, is really just the displacement field. It's just, what does the deformation look like? And if you know how this kind of body has deformed and expressed in terms of the displacement field, then you know everything else. You don't need to necessarily treat the strain field and the stress field as independent solution fields. And that's kind of convenient if you don't want to have to, independently figure out what those need to be. Most, finite element programs and other kinds of like automated solution approaches for solving these types of problems take exactly this kind of course of action. They reduce everything down, all of the solution unknowns down into just displacements. And then these other quantities are just kind of post-processing extra stuff that you get for free after you've solved the problem, as shown on the right-hand side. So ultimately, we're solving problems that kind of look like this. It's something that kind of looks a little nasty, right? There's these two kind of partial derivative terms. And in fact, this expression, this differential equation, is a second order differential equation expressed in terms of the displacement field. And remember, it's really a vector. It's the same as this equation, except we've just made a bunch of substitutions. And it's also important to note that this isn't really just three equations. This is a statement of equilibrium, which must be satisfied at every stinking point in the domain. So at every single, location or every single small chunk of material that we could look at in the domain, this equation has to be satisfied there and everywhere. So really, you could say that there's only three equations, but in reality, there's as many equations as you have points in the domain, which implies if there's, an uncountably infinite number of points to consider, then really there's an infinite number of these equations that we have to solve. That's pretty intimidating, especially because, well, we don't have an infinite amount of time to solve these problems. But there are kind of clever ways that you can go about solving these and, reduce the size of the problem into something more tractable. So we'll talk a little bit about how we do that and how exactly we solve these problems. But before we dive into those details, we need to introduce a few definitions. So first of all, these equations are really not the end of the story. Certainly, if we can express everything in terms of this one governing differential equation, which basically tells us, how do the displacements relate to strains and the strains relate to stresses, and how are those stresses in equilibrium with the applied external loads, we can express all of that in terms of this kind of differential equation. a pointwise statement of equilibrium at every point in the domain, but it really only tells us what's going on inside of the domain. It tells us what's happening if we were to look at individual points like hacked out of the center of some kind of larger body. But it tells us nothing about what's going on the boundary of this domain. And to really fully define and precisely define a given problem, set it up and have it have like a solution that we actually ascribe value to, we need to be precise about what is happening on the boundary. This is enough to characterize what's happening inside of it, but we need boundary conditions, basically additional constraints or extra equations that impose specific constraints or values on what the displacement field should look like on the boundary, or in some cases, what the prescribed values or components of stress should look like on the boundary. Now, it's important to note that at least in this expression, most of these quantities are known. In general, you kind of proceed in solving these problems, assuming you know what the material behavior looks like. You can quantify what are the elastic constants in terms of the material properties. You can also say, well, I know what the distributed load should look like applied to this body. The thing you don't know is the displacement field. So really, when you pose these kinds of boundary value problems, it's a statement of trying to find what is the displacement field, which satisfies this equation and some extra boundary conditions. And what do I exactly mean by boundary conditions? Well, take a look at our trusty old continuum potato just for reference. Suppose I had my continuum potato in my usual configuration. It's maybe resting on some kind of support represented in blue, and I can call that kind of support location, let's say, call it gamma u, which is kind of the portion of the boundary on which we will, let's say, purposefully constrain the displacements. So on this subset of the boundary, gamma u, let's suppose that we impose this boundary condition on the displacement field directly. We'll call it u equals u bar, where u bar with a bar over it means it's a prescribed value. It's a value that I'm telling you what it is, or you're telling the problem what it is. And it could be 0, it could be some kind of prescribed value, it's whatever you want. But it's a constrained value. It's a constraint that you're imposing on what the value of the displacement field should be along that kind of edge gamma u. And along the rest of the body, anywhere that we're not constraining displacements, it's basically implied that we're constraining the value of traction on that exterior part of the body. So that could be maybe due to some kind of external load. So for example, at the top right here, we have a particular example of a traction boundary condition, which basically is an imposition on the particular values of the stress exposed on this part of the surface. And we can determine what, again, using Cauchy's stress theorem, we can use that to determine what are the components of traction along this kind of surface. It'll vary with basically the exposed surface normal on that kind of portion of the boundary. And we can say, let's impose some kind of traction, which is really just a force per unit area. So it's a vector. And it basically means we can only really constrain or impose constraints on 3 components of stress, those that are exposed on this kind of exterior surface of the body. So we can impose traction boundary conditions that basically say that whatever components of stress are exposed on this surface have to be, equal to some prescribed value. And anywhere else where we're not specifically saying that it's equal to T bar, some prescribed value of traction, it's kind of assumed that, if we're not constraining displacement, we're not kind of putting any load on it, those extra areas on the rest of the body are kind of free surfaces. But in reality, they are still subject to traction boundary conditions. In fact, what you see in terms of these kind of like displacement boundary conditions and traction boundary conditions with a prescribed load, what you see is just as important as what you don't see. So in fact, anywhere that you're not assigning some kind of load or where you're not assigning some kind of displacement boundary condition, you're still assigning a traction boundary condition or a constraint on what the value of traction should be. It just so happens that the values of traction are just 0. Doesn't mean that it's not important to consider, because in fact, you have to define boundary conditions everywhere on the exterior of the body. Either you have to define a displacement boundary condition, or you have to define a traction boundary condition. Has to be one or the other. It can be zero. You can define a zero traction. That's totally fine. It just corresponds to this case of a free surface. But it's important to build that particular consideration into the solution of these problems. So when we're defining a boundary value problem, we really need to include all these different things. Really, a boundary value problem is just a statement of, a problem that we're trying to solve to determine some solution field, let's say the displacement field, which satisfies some governing differential equation, the equations of equilibrium, expressed in terms of this simplified representation of only unknown displacements, which has to be satisfied everywhere inside the body. And we also have to satisfy these extra boundary conditions. Any displacement boundary conditions that we prescribed on the part of the boundary where, we're basically constraining the movement of the body, or traction boundary conditions, anywhere that we're applying some kind of, traction or distributed load on the surface, or really anywhere that we're, allowing that surface to be free. So not constrained against displacement, but not also, applying any discrete load. So boundary value problems really encompass the definition of both of these things. And to give you a particular example, let's suppose you had this particular, cube of material. And let's not do cubes. Let's actually make it even simpler. Let's suppose it's just a two-dimensional block. And in this case, I can define boundary conditions on each of these different four faces of this two-dimensional block. Let's say on the bottom face, I'll fully constrain displacement in both the x and y directions. That's kind of like a fully fixed boundary condition, where the full vector of displacements is just fixed. You're disallowing transverse displacement and normal displacement relative to that bottom surface. On the left surface, let's kind of put some rollers in there, just, make it fun, which basically implies that we'll disallow normal displacement. Maybe it allows there to be some kind of normal kind of like tensile stress to develop, so it doesn't uplift or anything like that. So it basically prevents any kind of normal displacement, but also, we're not necessarily constraining transverse displacement. So in that case, we can kind of make it look like only constrain ux, the component of displacement, basically normal to that surface, but then just let it slide freely along that kind of vertical plane. And, implicitly what we're doing is we're kind of saying that, we're not prescribing the displacement in the y direction. But if we're not prescribing displacement in the y direction, we actually have to supplement this boundary condition with some additional statement that, well, really the shear stress exposed on this surface has to be equal to 0. That's equivalent to saying that there's really no way for us to kind of resist the sliding. And if that's the case, then truly there is no shear stress that should develop on that surface. If it's allowed to slide, there's no transverse shear stresses that could develop. Other places on the body where there's no stresses applied, such as on the top face, basically we'll have 0 values of these prescribed values of stress. In particular, the normal stress in the vertical direction exposed on that top face corresponds to the sigma yy stress, right? It's the component of stress acting in the vertical direction, exposed on that top face. And if there's no traction applied to that surface, it implies that along that surface, sigma yy, the vertical component of stress, is going to be equal to 0 along that full top edge. Same thing for the component of shear stress acting on that top face, the sigma yx component of stress. That also has to be 0. And then finally, if we're applying a load, maybe that has components of stress both in the x and y directions, maybe it varies spatially and does some other interesting things, then we can kind of represent these prescribed values of traction. In this case, the x component of traction, or basically the component of xx stress, exposed on this kind of x-facing cut of this block, and also the xy stress, the shear face on that exterior face. So anywhere that we're kind of exposing the surface, we can make direct constraints on the components of stress exposed on those surfaces. But for example, on this top face, we cannot prescribe the value of XX stress. That is not admissible in terms of how we define these boundary conditions. And the reason has to do with the fact that really, if you can only push on the surface or kind of like impose some kind of shear force on the surface, there's no way that you can directly control, the longitudinal stress that's going to develop like along the surface, basically. The membrane stresses are going to be what they are. There's no way that you can directly control those by applied loads. So really, it's only the components of stress exposed on these surfaces that you can have any control over. All right. So that's kind of a simple example of a boundary value problem. Now, one interesting aspect of boundary value problems is that, mathematicians like to overanalyze things, and they love to come up with these definitions. But in this case, I think the mathematicians, they were onto something, because they came up with these definitions of what constitutes a so-called well-posed boundary value problem. And what do we mean by a well-posed problem? Well, basically, it really can be broken down into 3 different criteria. For a boundary value problem, kind of like the ones that we were just looking at, such a problem is well-posed if it satisfies these 3 different conditions. If it satisfies this existence condition, which basically implies that the problem has to have a solution. If you're trying to set up a problem that somehow doesn't have a solution, then you're setting yourself up for failure. You don't want to try to solve a problem that doesn't have a solution, because you're not going to get anywhere. So you want to make sure that you're going to solve a problem that you're going to actually have a solution for. The problem has to be unique, or in other words, there can't just be one valid solution, or rather, there can't be more than one valid solution in order for this solution uniqueness to be valid. So you want to know that there is at least one valid solution. And ideally, you also want there to be only one particular unique solution that satisfies all these different constraints that you've put on the problem. If there's more than one solution, then it's kind of like, well, I don't know. How do we, which one do we pick? It's kind of like you don't have any path forward, or kind of, there's no reason you would pick one solution over another. So you want there to be a unique solution. And then stability, which we'll kind of gloss over. It's, we'll revisit the subject of stability later, but really just focus on existence and uniqueness, that there has to be a solution, and ideally that solution should be unique. Now, practically what this means in the context of solving these types of boundary value problems is that existence really implies that you can't over-constrain your problem. And in particular, you can't over-prescribe boundary conditions on this problem. So for example, we'll take the same problem that we had previously, but we'll make some modifications. Specifically on this left edge, where originally we were prescribing the component of normal displacement, or the displacement in the x direction. Let's suppose we also came around and said, well, hey, why don't we try doing this? Let's also prescribe the component of normal stress, or the XX stress, on that same face. Basically, this is equivalent to saying, I'm going to prescribe what the reaction force should be, in addition to also prescribing what the displacement should be at this point. That's just simply not possible. And it's kind of hard to actually see why that's the case, but suffice it to say, if you duplicate constraints or have these kinds of conflicting constraints on the problem, like so, where you're trying to apply both a displacement boundary condition and a stress boundary condition in the same kind of direction, then it will basically lead to, over constraint on your overall problem. And it'll make it such that there is no solution which actually satisfies these boundary conditions, because they're conflicting. You can't actually satisfy both of these things simultaneously. So you have to pick one. You can't have them both. So anywhere that you prescribe displacement on the boundary, in that same direction, you can't also prescribe stress. And that's true for all these other surfaces. Another particular example that I'll point to is in the case of solution uniqueness. If you have, let's say, the following example, where maybe I've modified some of the boundary conditions, and I'm not, over constraining the problem anymore, but you can kind of pretty obviously see what's wrong with this image, right? What's going to happen if I just let this kind of block go? After I apply these loads, what's going to happen to it? it's just going to fly off. There's nothing constraining this thing from just rolling on those rollers all the way to infinity and beyond. So in this case, we don't have a unique solution because we're not sufficiently constraining the body against rigid motion. So really, you can encapsulate all these different conditions into, a few constraints that you have to impose on how you prescribe the boundary conditions for a given problem. So in particular, if you want to avoid that issue of conflicting constraints or over-constraint, or in other words, if you want to ensure the existence of a solution, then you have to ensure that, as I mentioned before, you can't prescribe the value of displacement and traction in the same direction at the same point on a given portion of the boundary. You have to pick one or the other. It's one or the other. Either you constrain displacement in that direction or you constrain the traction in that direction, but you can't have both. Otherwise, you won't have solution existence. And for the case of solution uniqueness, this one's maybe a little bit more intuitive. But the idea is you just need to ensure that the body is sufficiently supported to prevent rigid motions. So you could think of it as simply supported constraints or supports. You have to ensure that the body's not going to translate or rotate once you put the loads on it. Fairly straightforward. Hopefully that's good enough. But there's some other stuff we have to do here. We also have to ensure that anywhere that we're putting constraints on the boundary, we have to basically be specific about like the value of displacement or traction that we're prescribing on the full boundary. So anywhere on the boundary, we need to have a displacement or a traction boundary condition. So if I have displacements constrained on the bottom, I have to basically say, what those values are. If I have tractions prescribed on the boundary, I have to say where those are. And basically, if there's any missing portions of the boundary where I'm not specifically constraining displacement or traction, that will actually violate this condition of solution uniqueness. I have to be explicit, even in the locations where there is no load applied or there's no kind of displacement constraints applied. Technically speaking, there is still a traction boundary condition applied there. It's just zero traction. So really, everywhere on the boundary needs to have either a displacement or a traction boundary condition, but it cannot have both at the same location. So that's kind of a nice way of encapsulating things. We'll dive more into the exercise, which I'll leave you with next time. This is kind of more of a puzzler. We'll give you the answer to these questions. Which of these different configurations satisfies all of those different conditions of solution uniqueness and solution existence? The answer next time. All right, I'll see you all then on Thursday.